The Bohr model for one electron atoms states that electron orbits are stable only with certain radii. The radii are given by r equals a0 times n squared over z, where a0 is the Bohr radius given by 4 pi epsilon 0 divided by e squared times h bar squared over me. N squared, n is an integer and it's a quantum number, and z is the nuclear charge. Now, what's the total energy of the electron in such an orbit with radius r? It's of course the sum of the kinetic energy, E kin, plus the potential energy, E pot, or more commonly denoted as T for the kinetic energy plus V for the potential energy. The kinetic energy is 1/2 me v squared, and the potential energy is minus 1/4 pi epsilon 0 times z e squared over r. Now recall the force balance in an orbit. The electrostatic attractive force must be equal to the centrifugal. The attractive force is 1/4 pi epsilon 0 times z e squared over r squared, and this force must be equal to the centrifugal force me v squared over r. We can use this expression to substitute it into the kinetic energy. Kinetic energy contains me v squared, and the centrifugal force contains me v squared. Therefore, we can use the left-hand side expression. So we get 1/2 times z e squared over 4 pi epsilon 0 r, that's the kinetic energy, minus, and now we copy the potential energy, 1/4 pi epsilon 0 times z e squared over r. The two expressions in the parentheses are identical. So therefore we get in the end minus 1/2 times z e squared over 4 pi epsilon 0 r. Now let's substitute in r from our first expression on the top left. We get minus z e squared over 8 pi epsilon 0 times z e squared over 4 pi epsilon 0 times me over h bar squared n squared, which simplifies to minus me over 2h bar squared times z e squared divided by 4 pi epsilon 0 parenthesis squared times 1 over n squared. This prefactor here consists only of physical constants and the nuclear charge. For z equals 1, it's equal to 13.6 electron volts. So finally we can write for the energy as a function of the quantum number n that it is equal to negative 13.6 electron volts times z squared over n squared. This is the central result of the Bohr model. It shows that the energy is quantized and that it depends on the quantum number n in a 1 over n squared fashion. Only the orbits with these energies are stable. We speak of stationary states and energy levels. Let's look at the energy levels for hydrogen. All energies are smaller than 0. All energies are negative. The lowest energy level for the lowest lying state is at minus 13.6 electron volts. It corresponds to n equals 1, and the radius is A0. The next higher level is n equals 2 and has a radius of 4A0 and an energy of negative 3.4 electron volts. One level up with n equals 3 and a radius of 9A0 has an energy of minus 1.5. This continues with ever closer spacings, energy spacings between the different states until they converge to 0. Transitions between these states occur via absorption or emission of photons. The energy of an emitted or absorbed photon must match the energy difference between two states. Let's calculate that. Let's look at two states with quantum numbers n1 and n2, where n2 is larger than n1. The energy difference, delta E, between those two state energies equals En2 minus E subscript n1. And it is me over 2 h bar squared times ze squared over 4 pi epsilon 0 squared times 1 over n1 squared minus 1 over n2 squared. Notice that the order of n2 and n1 has changed because we have absorbed the negative sign from the original energy expression into the difference expression. Now, in order for photon absorption to occur, this energy difference, delta E, has to match the photon energy, h nu, or in wave numbers, h c nu tilde. Rearranging this, we get nu tilde equals 1 over hc times me divided by 2 h bar squared times ze squared over 4 pi epsilon 0 squared times, and then in parentheses, the quantum number expression 1 over n1 squared minus 1 over n2 squared. This prefactor here, that contains only fundamental constants and the nuclear charge, equals to the Rydberg constant for the hydrogen atom. That is when Z equals 1. This is amazing. The Bohr model basically is able to explain the hydrogen emission spectrum. In fact, the Lyman series in the ultraviolet corresponds to emissions from excited states down to the ground state with n equal 1. The Balmer series in the visible range corresponds to emissions down to the level of n equals 2 from higher excited levels. And the Paschen series that's in the infrared involves transitions down into the n equals 3 state. This is all very exciting. However, the Bohr model is valid only for 1 electron atoms. These atoms include hydrogen, as we've just discussed, but also helium plus, not a very common ion, and lithium 2 plus, even less common. Beyond these 3 ions, the Bohr model is not valid. It is not valid for the entire periodic table. Therefore, it's extremely limited, and we need a much better theory to explain the structure of atoms.